the evening of March 27, 1964, settled over coastal Alaska with the particular stillness that comes before a holiday weekend. In Valdez, the harbor reflected the last amber light of late afternoon. Fishing boats rocked gently against their moorings. In Seward, shop owners locked their doors and turned toward home. The smell of cold salt water mixed with diesel exhaust from idling engines along the docks. Across the coast, from Cordova to Kodiak Island, the rhythms were similar. Small towns built on the edge of deep water. Communities that existed because of the sea, clustered around natural harbors where the mountains dropped steeply into fjords. These were places where the Pacific pressed against the land with geological insistence, carving inlets that stretched miles inland, creating shorelines of dramatic verticality. The region's topography was a product of millions of years of tectonic collision. Steep coastal mountains rose directly from tidewater. Glacial valleys had been drowned by rising seas, forming the long, narrow arms of Prince William Sound. Tidal ranges here were substantial, exposing vast mudflats twice daily, revealing the temporary nature of the boundary between land and water. On this particular Friday, none of this registered as unusual. Families prepared for Easter weekend. Children were out of school. In Anchorage, 120 miles from the coast, the J.C. Penney store was crowded with shoppers. Along the waterfront communities, longshoremen finished their shifts. Warehouse lights blinked on as dusk approached. The temperature hovered just above freezing. Snow still covered the upper slopes of the Chugach Mountains. The water in the harbors was calm, undisturbed by wind. Seabirds settled on pilings. Smoke rose straight from chimneys into the clear air. This ordinariness would be remembered later, documented in dozens of witness accounts. The specific quality of the quiet, the lack of any atmospheric warning, just another Friday evening in late March, indistinguishable from any other until it wasn't. Beneath the apparently stable landscape of south-central Alaska, a geological process had been continuing for millions of years. The Pacific Plate, a vast section of the Earth's crust underlying the ocean, was being driven eastward and downward beneath the North American plate at a rate of approximately 2 inches per year. This subduction zone extended in a broad arc from the Alaska Peninsula through Prince William Sound and down the coast toward British Columbia. The descending oceanic plate generated enormous compressional forces as it ground beneath the continental margin. Over decades, the upper plate bent downward, storing elastic energy like a compressed spring. The coastline was therefore not geologically stable, though it appeared so to human observation. The land itself was gradually being pulled downward by the locked interface between the plates. This deformation was measurable, but had not been adequately documented before 1964. Geodetic surveys were sparse in this remote region. The infrastructure of coastal Alaska reflected no awareness of this underlying instability. Valdez sat at the head of a steep-sided fjord on an alluvial fan of glacial sediment. The town's waterfront was built on unconsolidated material deposited by the low river. Wharves extended on wooden pilings driven into this loose substrate. Seward occupied similar terrain at the head of Resurrection Bay. Its harbor facilities, rail yards, and fuel storage tanks were concentrated on a narrow strip between the mountains and deep water. The Alaska Railroad terminated here, making it a critical shipping hub. Petroleum products were stored in large cylindrical tanks positioned close to the shoreline. Whittier, accessible only by rail tunnel through the mountains, was built almost entirely at sea level on the flat delta of Passage Canal. Military facilities and civilian docks occupied this constrained space. Kodiak, on its namesake island, had a substantial fishing fleet and Coast Guard station positioned along the waterfront. None of these communities had building codes accounting for seismic risk. Construction was wood frame, pragmatic, designed for the climate but not for ground acceleration or sudden changes in elevation. The relationship between the towns and the water was intimate and unprotected. Houses faced the harbors. Streets ran perpendicular to the shore. Critical infrastructure occupied the lowest, most accessible ground. The vulnerability was structural, geographic, and geological. It existed in the composition of the sediments, in the proximity to deep water, in the steep submarine slopes just offshore, and in the fundamental tectonic architecture of the region. At 5:36 p.m. Alaska Standard Time, the locked interface between the Pacific and North American plates released. The rupture initiated at a depth of approximately 15 miles beneath Prince William Sound and propagated along a fault zone extending roughly 500 miles from southwest to northeast. The earthquake lasted between 3 and 5 minutes, depending on location. This extraordinary duration was a function of the rupture length. As the fault continued to slip, seismic waves continued to radiate outward. The ground did not shake violently in sharp jolts, but rather rolled in sustained, disorienting motion. In Anchorage, buildings swayed rhythmically. The ground appeared to move in waves. Witnesses described a sensation of fluidity, as if solid earth had become temporarily liquid. The Turnagain Heights neighborhood, built on a bluff of glacial clay, began to slide toward the ocean in massive blocks. Entire streets broke apart and descended in terraces. Along the coast, the motion was accompanied by immediate vertical displacement. Sections of shoreline dropped as much as 8 feet in seconds. In Portage, southeast of Anchorage, the land subsided below the high tide line, permanently flooding forests and roads. Trees that had stood above the water for centuries now rose from salt water, their roots submerged. Other areas experienced uplift. Parts of Montague Island rose 38 feet. Entire sections of seafloor that had been underwater were suddenly exposed to air, with barnacles and marine organisms left stranded on newly elevated rock. This vertical reorganization of the landscape was measurable and documented. U.S. Geological Survey teams would later map the deformation in detail. The pattern showed classic subduction earthquake behavior, coastal subsidence in areas above the locked zone, and uplift farther seaward where the overriding plate rebounded. In Valdez, the shaking triggered submarine landslides. The unstable sediments of the delta front failed and slid into the fjord. The town's waterfront, including the dock where a ship was moored, disappeared into the water. In Seward, similar failures occurred along the harbor front. The combination of ground motion and sediment liquefaction caused sections of the developed waterfront to collapse and sink. Structures did not collapse dramatically. They tilted, settled, separated at joints. Wood frame buildings proved resilient to the shaking itself. The damage came instead from the ground failing beneath them, from foundations losing support, from the sudden absence of solid substrate. The earthquake registered 9.2 on the moment magnitude scale, making it the second largest instrumentally recorded earthquake in history at that time. The energy released was equivalent to approximately 240 megatons of TNT, but the human experience was not of explosion. It was of prolonged, inescapable motion, and of the ground behaving in ways that contradicted all expectation. When sections of seafloor suddenly rise or fall across hundreds of square miles, the water column above them must adjust to this new geometry. The displacement generates waves that propagate outward from the source region, traveling at speeds determined by water depth. In the deep Pacific, tsunami waves moved at approximately 500 miles per hour but remained nearly imperceptible at the surface, with wave heights of perhaps a few feet spread across wavelengths of many miles. As these waves approached shallower coastal waters, their speed decreased and their amplitude increased dramatically. The subsidence of coastal areas around Prince William Sound created complex local conditions. In some locations, the immediate effect of land dropping was that the water level appeared to rise, flooding areas that had been dry. But the displacement of the seafloor also generated outward propagating waves that would return to these same coasts within minutes. In areas where land had risen, the initial observation was of water retreating, harbors partially drained. The seafloor became visible. This withdrawal was not the tsunami itself, but the trough preceding the first wave. The water was being drawn into the displaced volume created by the subsided areas. The wave generation was not a single event, but a series of pulses. Submarine landslides triggered by the earthquake created additional local waves. In Valdez, the collapse of the delta front generated a wave that struck the remaining waterfront within minutes. Survivors reported water surging upward against the town, carrying debris from the collapsed dock. The physics were straightforward, but the effects were compounded by geography. Fjords acted as wave guides, funneling energy toward their heads. Narrow inlets amplified wave heights through resonance. The steep underwater topography caused waves to steepen rapidly as they shoaled. The first waves often arrived within 10 to 15 minutes of the earthquake in nearby communities. Subsequent waves continued for hours as the energy dispersed and reflected throughout the complex coastline. Each bay and inlet had its own pattern of arrival times and amplitudes depending on its orientation, depth, and geometry. The water moved as a surge rather than a breaking wave. It rose rapidly, flooding inland, carrying whatever it encountered. When it withdrew, it pulled material back toward the sea. The cycles repeated with varying intensity. Some waves were larger than others due to interference patterns and reflections from underwater topography. This was hydraulic reorganization driven by gravity, the ocean surface seeking equilibrium with a suddenly altered seafloor. There was no malice in it, no intent, only the mechanical response of fluid to displacement, constrained by the shape of the coastline and the depth of the water. In Valdez, the waterfront no longer existed. The submarine landslide had taken it, and the subsequent waves moved through a town already destabilized by subsidence. Water reached several blocks inland. The SS China, docked at the time of the earthquake, survived the initial landslide but was carried by the waves. 32 people who had been on or near the dock were missing, presumed drowned. Seward's Harbor faced multiple threats simultaneously. The earthquake caused immediate waterfront collapse. Fuel tanks ruptured and spilled petroleum products into the water. When the tsunami arrived, it carried burning fuel inland. The combination of water, fire, and debris moved through the rail yards and residential areas nearest the shore. The town's economic center was destroyed. 13 people died. Whittier's confined geography offered no high ground for evacuation. The waves moved through the narrow delta with concentrated force. The Hodge Building and the Buckner Building, large military structures, survived, but smaller buildings near the waterfront were demolished. The railroad facilities were heavily damaged. 13 deaths were recorded. Kodiak, farther from the epicenter, had more warning time, though warnings were not effectively disseminated. The waves arrived after dark, complicating evacuation. The downtown waterfront was inundated. Boats were carried inland and deposited on streets. The fishing fleet suffered severe damage. The Coast Guard station recorded water heights of 20 feet above mean lower low water. Buildings on pilings collapsed when the supports were undermined. In each location, the pattern was similar. Infrastructure concentrated at the lowest elevation suffered the greatest damage. Wooden structures were lifted and displaced. Concrete foundations were undermined. Utilities were severed. Transportation connections were broken. The communities were not destroyed in the sense of complete annihilation, but their functional capacity was severely compromised. The casualty count was kept relatively low by the timing. The earthquake occurred during evening hours on a holiday weekend when commercial activity was reduced. Many people were at home rather than at work. In some areas, the duration of the earthquake itself provided warning, allowing people to move to higher ground before the waves arrived. In other locations, There was no warning and no time. The total death toll from tsunami inundation in Alaska was approximately 106. This represented about 80% of all earthquake-related fatalities. The ground shaking itself caused relatively few deaths due to the resilience of wood frame construction and the low population density of the affected region. The economic impact was substantial. Seward's port and rail facilities represented critical infrastructure for Alaska's economy. Valdez would eventually be relocated to a more geologically stable site. Whittier's isolation was compounded by the damage to its single rail access. Kodiak's fishing industry faced the loss of vessels and processing facilities. The physical alterations to the coastline were permanent. Subsided areas remained below their pre-earthquake elevation. New tidal regimes were established. Forests killed by saltwater intrusion became standing dead wood, bleached and skeletal. Navigation charts required revision. Harbor depths changed. The relationship between land and water had been fundamentally reconfigured. The tsunami propagated across the Pacific at predictable speeds, its arrival time at distant coasts calculable from the earthquake origin time and water depth. The waves reached British Columbia within hours. Washington and Oregon coastlines were struck during the night. Crescent City, California, positioned in a crescent-shaped bay that acts as a natural amplifier for tsunami energy, received the most severe impact outside Alaska. The first waves arrived around midnight. They were not particularly destructive, but the fourth wave, arriving near 1:45 a.m., reached heights estimated at 20 feet above mean sea level in the harbor area. The wave moved through the downtown waterfront district with sustained force. Buildings were pushed off their foundations. Vehicles were carried several blocks. The business district closest to the harbor was demolished. Logs from the waterfront, used in the local timber industry, became battering rams in the surge. 11 people died in Crescent City. Some were in buildings they believed were safe. Others were outside, unaware of the continuing danger after earlier waves had receded. The damage was concentrated but severe. 29 blocks of the downtown area were affected. 289 buildings were destroyed or damaged beyond repair. The amplification effect at Crescent City was well documented afterward. The bay's geometry focused tsunami energy, and the harbor's configuration created resonance effects that increased wave heights beyond what would be expected at open coast locations. This made the community particularly vulnerable to distant-source tsunamis. Other locations along the Pacific Northwest coast experienced less severe but still notable impacts. Flooding occurred at low-lying coastal areas in Oregon and Washington. Boats were damaged in harbors. Docks were destroyed. The waves were large enough to be dangerous, but not large enough to penetrate far inland except in specific geographic configurations. The distance from Alaska meant that the tsunami energy had dispersed across the width of the Pacific. Wave heights decreased with distance from the source, but the wavelengths remained long, and the periods between waves were on the order of tens of minutes. This made the hazard persistent and difficult to predict. Hawaii received measurable waves, but experienced minimal damage due to the directivity of energy propagation from the Alaskan source region. Japan recorded the tsunami on tide gauges, but at reduced amplitude. The waves eventually dissipated as their energy was absorbed through friction and spreading. The transoceanic propagation demonstrated the far-reaching effects of Great Subduction Zone earthquakes. A rupture in Alaska could generate hazardous waves thousands of miles away. This understanding would become central to the development of tsunami warning systems in the following decades. In the weeks following the earthquake, the altered landscape became fully apparent. The subsided forests near Portage stood in saltwater at high tide, gradually dying as their root systems were poisoned by salinity. These drowned trees would remain standing for decades, a visible marker of permanent elevation change. Coastal communities faced immediate challenges. Roads were broken by landslides and ground failure. Bridges had collapsed or were rendered unsafe. The Alaska Railroad, critical for transportation between Anchorage and Seward, required extensive reconstruction. Communication systems were disrupted. Electric power was unavailable in many areas. Federal and military response began quickly, but was hampered by accessibility issues. The remoteness of Alaska and the extent of infrastructure damage meant that relief supplies had to be airlifted. Temporary housing was established for displaced residents. Engineers began assessing the stability of damaged structures and the viability of rebuilding in affected locations. The decision to relocate Valdez was made after geotechnical studies confirmed that the original townsite remained vulnerable to future landslides. The new town was established 4 miles away on more competent bedrock. This relocation took several years and required complete reconstruction of civic infrastructure. Scientific investigations began immediately. The U.S. Geological Survey deployed teams to measure ground deformation, map fault rupture, and document tsunami run-up heights. Seismologists analyzed the earthquake's characteristics. The event provided unprecedented data on the behavior of Great Subduction Zone earthquakes. One significant outcome was the establishment of the West Coast and Alaska Tsunami Warning Center in 1967, initially called the Alaska Tsunami Warning Center. This facility, located in Palmer, Alaska, was tasked with monitoring seismic activity and issuing warnings for tsunamis generated in the Pacific. The 1964 event had demonstrated that even with a few hours of travel time, effective warnings required rapid detection and communication systems. Building codes in Alaska were revised to account for seismic risk. Engineers developed new standards for construction in earthquake-prone areas. The field of earthquake engineering advanced considerably through analysis of structural performance during the event. The concept of designing for ground failure, not just ground shaking, became more prominent. The earthquake also contributed to the acceptance of plate tectonic theory, which was still being debated in 1964. The pattern of uplift and subsidence, the location of the rupture zone, and the relationship to the Aleutian Trench all supported the model of subduction and elastic rebound. The Alaska earthquake became a key case study in tectonic processes. For the communities directly affected, recovery was slow. Economic activity depended on functional ports and transportation links. Rebuilding required capital investment at a time when the local economy had been disrupted. Some residents chose not to return. Others remained and participated in reconstruction. The coastline itself settled into new patterns. Tidal ranges adjusted to the new land elevations. Harbors required dredging or relocation. Navigation hazards appeared where uplift had raised seafloor features. Biological communities in the intertidal zone adjusted to altered conditions. Decades later, the evidence remains visible. The dead trees near Portage still stand, though increasingly weathered. Valdez exists in its relocated position. In Anchorage, the Turnagain Heights landslide area was partially developed again, though with restrictions. Seismic building codes have been repeatedly updated based on evolving understanding of earthquake risk. The 1964 Alaska earthquake and tsunami demonstrated the capacity of geologic processes to reorganize the landscape at scales that dwarf human infrastructure. The rupture lasted minutes. The waves dissipated over hours. But the consequences persisted for decades and continue to shape policy and planning in seismically active regions. The coastline is quiet again, as it was on that Good Friday evening. But the quiet now carries a different quality of awareness. The stability of the ground is understood to be temporary, contingent on the ongoing collision of tectonic plates beneath the surface. The ocean is recognized as capable of responding with sudden violence to these deep earth processes. The boundary between land and water is acknowledged as fundamentally unstable, subject to forces operating on geologic timescales that occasionally intersect with human time in moments of catastrophic realignment.